Thank you for the introduction. And today I will be talking about annular permutations in non-commutative probability. So I was hoping to give a talk for everybody. So I'll start with very basic stuff. Uh, so I will consider just the matrix setup, a random matrix setup. I'll just take a square random matrix with entries ij. I'm gonna consider there, in this case, a real. Also, I could also consider a complex matrix. I'm gonna impose the condition that it is self-adjoint. For if I only have real entries, then that means that xn equals to its transpose. If I have complex, then I will add the complex conjugate there. I do this so I can talk about the eigenvalues of my random matrix. And something that I will be interested in looking at is the eigenvalue distribution. So this is very standard from random matrix theory. And a way of looking at the limited eigenvalue distribution is that I look at the expected value of the trace of k powers of my random matrix. And I normalize by the size of the matrix, and then I let n go to infinity. And then I'm gonna say that I have a limit in eigenvalue if this quantity converges to the kth moment of limiting measure. I'm gonna call that the kth moment. And also know that, well, the trace is just computing the kth powers also of the eigenvalues. So in a sense, I'm just computing the expected value of the kth powers of the eigenvalues. Okay, another thing that is going to be related to annular non-crossing permutations is something that was referred to by Octavio, and this is real-rooted polynomials. In this case, we just have a real-rooted polynomial of degree n, that's a monic polynomial. Here, I just put the roots of my polynomial. Of course, there is a dependence on Pn, but usually it is assumed, but I will not write that dependence. And again, I analyze now the limiting root distribution by just taking the average of the kth powers of the roots of the polynomial. I'm gonna say that this has a limiting root distribution. Again, when I let n go to infinity, that coincides with the kth moments of a limiting measure. Note that these kth powers are also the kth moments of this discrete measure. Then, having those two objects, I could ask, well, in some cases, it turns out that this normalized trace has an expression of the form, so essentially has an expansion of 1 over n, where the constant term is the kth moment of my limiting measure, and then the second correction term is what some people call the infinitesimal moment there. This happens for several models in random matrices. And then I have an initial term such that when I multiply it by n and I let n go to infinity, that goes to 0. The correction term here, usually it is expressed as a sign measure, just a difference of two positive measures. And something similar happens for the polynomials. Essentially, the kth moment of my polynomial can be expressed as the kth limiting moment plus a correction term of order. Just an example, like a very trivial example. And also, sometimes I don't usually take the exact dimension as n. Sometimes n just index the dimension, and the dimension goes to infinity. As an example, when you have this, like a very easy example, when you have this limiting distribution and infinitesimal, I think I didn't say that, but these guys here are called the infinitesimal moments, and this guy here, this mu prime, is called the infinitesimal distribution. Okay, as a toy example, but illustratively, yet it's just take this x minus 1 to power n and x plus 2 to power n. We know that the roots are just plus and minus 1, and then add two additional roots. It turns out that for this guy here, the limiting measure is just the Bernoulli symmetric in plus 2 negative 2. And then infinitesimal distribution is this discrete measure, delta alpha plus delta beta, beta minus 2 times delta 0. I think the idea with something that we can get from this is that infinitesimal distributions detect small perturbations. And by small, I mean perturbations of order 1 over n in the way we converge to limiting distributions. Okay, another thing that I will consider and where annular permutation will come up is global fluctuations or covariance of traces of random matrices. In this case, I just consider the covariance of the trace of my random matrix to the kth power and the trace of my random matrix to the lth power. And well, the covariance, I will assume that the entries of my random matrix have moments of all orders. So I can express this covariance as the expected value of a product of traces minus the expected value, the product of the expected values of each trace. Okay, so now the question is, what do infinitesimal distribution and global fluctuations have in common? And I guess since this is a talk about annular permutations, is not surprised that, well, the answer is non-crossing annular permutations. Now, I will try to tell you, give you like an intuition of why annular permutations come in a very natural way, at least for the global fluctuations. And the reason for that is actually pretty simple. We can express the trace of a matrix. Well, it's just the sum of the diagonal entries. One thing that I think I did not emphasize, but it is something that we do, is that we normalize the entries by 1 over square root of n. Okay, when we do that and consider the trace of the kth power, well, it comes out the factor of 1 over power k over 2. And then I'm just summing the diagonal entries of my kth power. Then I can express that as a product of entries where the adjacent indices are the same, and also the first and the last indices. I'll do the same for the lth power now, but I will use these indices, and instead of having I1, well, started from I1, I will start from ik plus 1, and I'll go all the way up to k plus l. Now, this is very basic. This is just a very basic calculation. Remember, I want to analyze the covariance. That's the expected value, well, the expected value of some product minus minus the product of some expected values. So I just expand out my trace. I relabel each of the entries in this product as variables y1, y2, and so on. So it gets this very simple expression. Of course, the y's depends on the indices I. So far, I haven't assumed anything about the random matrices, so all of this is in general. And before telling you the next step, let me define this partition, gamma. So gamma is a partition of 2 cycles. One goes from, one cycle goes from 1 up to k, and then the second cycle goes from k plus 1 all the way up to k plus l. And then I'm going to define 2 partitions on the set of k plus l elements. And the partitions are defined in terms of, well, the first partition is defined by the relation, well, S is related to T if and only if IS is equal to IT. So this is given a sequence I1, I2 of indices I1, I2, IKL. Well, the kernel of I is just the sequence. It's defined by this relation, and something that should be noted, well, it just captures which indices are the same. So that's it. There is nothing very special there. Now, for the kernel, I'm also going to define another partition, which I'm going to define as the kernel of I gamma. And it's also a partition k plus l elements. And the condition now is that S and T are related if any of these 2 conditions are satisfied. Either IS equals IT and I of gamma S equals I of gamma t, or I of s equals I of gamma t, and I of gamma s. Okay. What this does, well, essentially, because I have my variables here, I'm basically, with the kernel of I, I'm just recognizing which indices are repeated here. And then with the kernel of gamma, I'm just grouping the same variables that appear here, because either I could have the variable ij as xij or ji. Good. One thing to notice is that the size of the kernel I gives a number of distinct values in my sequence, whereas the kernel of gamma I just groups the same variables appearing on my sequence y1 all the way up to this is just a bicyclic shift. This is just the same expression I had before. Now, this is where some assumptions come into play. Because one assumption that I'm gonna make about the entries of my random matrix is that they're centered, so they have expected value 0, and that because I have the symmetry given by the transpose, then an assumption that it is usually assumed is that the entries in the diagonal and the upper diagonal are independent and identically distributed. This is just the thing about the central limit theorem. Have the same identical IDD entries. Okay, so these conditions, like these two single conditions, are actually enough to tell something and for annular non-crossing permutations to appear. Why is that? Well, I said the kernel of I gives a number of distinct values on my sequence, whereas kernel of gamma I groups variables, the same variables that appear in this product. Now, by independence, the first expected value in my expression is just gonna be a product of expected values, and that's just by independence. And then the same for the second terms here, right? Now, let me see. Yeah, okay. So, when am I gonna get a 0 here? Because of centeredness, I will get a 0 here if the kernel of gamma I has a singleton, right? And if the kernel of gamma has a singleton, so does the restriction to the first k element and the restriction of that partition to the last L element. Crucial observation is that, well, this is just what I said. If this guy has a singleton, this whole thing vanishes. And then one can show that if the kernel of I has a singleton, so does the kernel of gamma of I. Moreover, if I have an invariance of the kernels, if I have two sequences I and I prime, then the corresponding kernels of gamma are the same. Okay? Then that does the trick, because that does the trick, because essentially by these relations here, and now the independence and the fact that they are identically distributed, this term here only depends on the kernel of gamma. I can group indices with respect to the kernel of I. Now I can put a partition here and group all the indices if they have the same kernel of I, and if they have the same kernel, then they will have the same expression here due to this property there. Yeah, so this guy here only depends on pi, where pi is the kernel of I, and then I can move this expression and group just my indices by its kernel. That's it. Questions so far? Okay, now this guy here only depends on pi. Then I just need to count all the indices that have the same kernel pi, and that's gonna have order n to the number of logs of pi. Okay? I just need to choose the value on each block. Of course, it'll be n plus n minus 1 all the way up to n minus but which partitions are allowed here? Well, I said that if the kernel y has a singleton, then this thing will vanish. So that means that I need to consider only partitions with at least 2 elements. But if a partition has, if I consider partitions that have, which each block has at least 2 elements and one block has at least 3 elements, then the number of blocks in total will be less than k plus L over 2. So I can only consider partitions that have exactly k plus 2 over 2 elements. That means that all partitions have to be parents. Okay, good. This is good. Now, there's something else there. I said this term here that only depends on pi. And what's going to happen if the partition do not connect things that are from the first k elements and the last elements? Well, by independence, this term will be exactly this term, because I'm not connecting, by independence, I'm not connecting things that are here to things that are here. So there is no contribution there either. So I must have at least one guy that goes from the first k elements to a guy that goes to the last L elements. Yeah, but then if I have that, because I only have pairings there, then when I consider the second term here, and because I only have pairings, then either this sequence has a singleton or this sequence has a singleton. So I really don't care about this guy anymore. So I will only consider the expected value of this product, or pairings that satisfy that connects one guy from here to another guy from there. Long story short, up to some more calculations, it leads to annular non-crossing permutation. It turns out that, there's a little bit more of work to do there. And essentially is that, well, I know that there is at least one guy connecting the first K to the last L. So let's say that's ST. And if these two guys are not the same entry, then again, I have a single entry, and that's going to be 0. And that gives you a recursion relation that at the end leads you to non-crossing annular permutations. In this case, only counts pairings. These two, because I assume my matrix was real, comes from that either I have this symmetry. If you assume complex, then you remove these two. This sigma is just the variance of one entry. Okay, for pairings, you can cut and then not become an but for pairings. Now, in general, for these non-crossing annular permutations, what we do is that we draw k points on a circle and L points in an inner circle. And there is an algebraic definition for these guys. Essentially, you consider all the permutations in k plus element, such that the sup with this gamma, remember this gamma has only 2 cycles, is the whole thing. And the second condition is just a geodesic condition. That says the number of blocks of pi plus its reverse complement. So here I have an annular non-crossing permutation. And then, as I said, this guy here is just the Kravers complement. Okay. Okay, so now what about infinitesimal distributions? So for infinitesimal distributions, one more thing. I should say that, I mean, the same ideas, you can just do the same ideas by replacing this power by product of independent matrices, right? So the only thing that's going to change is that now you will have an additional condition in which you will have to, like, basically you color your permutation, your partitions. Okay, for infinitesimal distributions, so what's going to happen is that I'm going to consider, so essentially I'm gonna consider SKL, but now I'm gonna put L equals to K. I'm gonna relabel the K plus 1 all the way up to K, which would go on the inner circle, as minus K plus 1 all the way up to minus N. Okay, but it's the same thing. I just relabeled the inner points. So that's this guy, SNC plus K minus K. And then for the delta, so are all those things that are there in SNC plus K minus K, but with two additional conditions. And the first condition is that S and minuses are never in the same cycle. And the second condition is that if I have a cycle there, then I have the opposite, the reverse cycle with opposite signs. Okay, that's just a symmetry condition. As an example, I have three guys here. This is not gonna be in this SNC delta because I have a block that connects 2 and minus 2, whereas the others, I don't have that condition. So here I have block 1, minus 2, minus 3, and then I have its symmetric image, which will be minus 1, 2, and 3. That's also I have 4 in its own and negative 4 in its own. Okay, what about these symmetric guys? And what do we care? Well, remember that I talked about infinitesimal laws. Well, it turns out that they appear in infinitesimal laws. Remember, this is just the usual limiting eigenvalue distribution for a random matrix. This is the infinitesimal distribution. For if I take xn equal to a Gaussian complex, that means that the integers are Gaussian, then, well, the infinitesimal moments are 0. But if I instead take the real Gaussian, then the infinitesimal moments are counted by these annular non-crossing pairings, well, these symmetric ones, and there is actually an explicit expression. This is work by Jamie. Well, in the two cases above, shown above, the eigenvalue distribution is just the semicircular. I think here I'm missing 1/2 pi. Okay, what else? Another cases where this shows up is in the complex Wishart. Well, no, not in the complex Wishart. This is just the complex Wishart is product of two rectangular matrix n by mn with complex Gaussian entries. There are some assumptions in which the rate of the size of this rectangular matrix grows, but essentially you can compute the infinitesimal moments. But it is in the real case where the matrix of the G matrix has real Gaussian entries that these annular non-crossing permutation appears. Yeah, it turns out that in this case I think this is the shape parameter, and you sum C to the number of logs of pi over 2, and you sum over all these non-crossing annular permutations. Symmetric ones, the symmetric ones. Okay, now this is work with Octavio Arismendi and Daniel Perales. Let me go back to the polynomial case. In the polynomial case, we said that, well, we have the finite moments for Pn, we have the limiting moments, and then we have the infinitesimal moments. It turns out that if we have the infinitesimal moments, then the finite precumulants have also an expression of 1/n, okay? These guys here are just the precumulants, usually, the usually precumulants, And these guys here are just some numbers that do not depend on n. Okay, the relation is that, well, we find a relation between the infinitesimal moments and these quantities, and which is given by this relation. Now this relation appears in infinitesimal free probability, although the only difference is that we replace what is the infinitesimal free moment by this r hat. And then again, we have this term there, which is related to the Markov-Chain transform. If you want to know more about this, it's essentially a function that depends on the Cauchy transform. Yeah, here I said similar. Oh, yeah, I should know this. This pi over 2 is just similar to the usual product of when you have a sequence, but because we have the symmetry here, we only take one block from each pair of symmetric cycles. Remember that I said that whenever you have a cycle, you have a symmetric reverse cycle with opposite signs. Okay, this is a nice picture. Essentially, it says that the symmetric annular permutations are captures copies of all non-crossing annular permutations. When I go from, well, if I consider the case, the size of the symmetric as k, then this is just the union of SC1, k minus 1. We have a very, Jim and I, we have a very specific bijection for this. And essentially the whole thing is that where you cut, you unfold, you relabel, and then you get a symmetric thing. Okay? And that allows us to prove some other relations. Finally, where does this object appear? Well, it's going to appear on the infinitesimal distribution of matrices. This is a work in progress, not mine, but with Jamie, with Guillaume Sebron. And this thing also appears in the infinitesimal distribution of finite free convolution. So here I'm looking at the infinitesimal moments when I take the finite free convolution of two polynomials that each of which has a limiting eigenvalue distribution with corresponding limiting infinitesimal distribution. So this is what you would get if you consider just infinitesimal freeness in the additive case, but then again you have this additional term there. And,